Next up, another reaction. Yeah, another reaction. Oh my goodness. Oh my god. Yeah, I know. They just keep coming, and that's just how organic is. And it's our job just to keep them separate and kind of understand the basics and figure out the best possible scenarios of when to use each one. So in this reaction, this one's called a hydroboration oxidation. Very similar to mercuric reduction, just kind of the flip version of it, right? Alkoxymercuration reduction. Except reduction, we've got oxidation, but it looks also like I have boron here in play as well. So hydroboration has to represent something, right? It does. So let's talk about the basics of hydroboration first before I show you an example of that reaction. Notice that in every time, in every case, we've talked about these reactions, and electrophile was very important. An electrophile is typically something positive. So water did not have an electrophile. We added acid. That was the positive piece. That jump-started the reaction and it helped it go forward. Alcohol really didn't have a good electrophile, so we added acid to that as well, and that acid was the positive piece that allowed it to go forward. The Br2, the Cl2, one of those bromines or one of those chlorines in that diatomic bond actually came onto the double bond, broke that double bond, and that served as the electrophile for those reactions. All right, so that's great. That's great. Not a big deal. Hydroboration oxidation also uses an electrophile. The electrophile here, though, is BH3. Now, BH3 does not carry a full bone positive, neither did bromine diatomic or chlorine diatomic molecule did. But BH3 was one of these pieces way back when we talked about nucleophiles and electrophiles, and we identified them. BH3 was one of those that they got us to identify, and this is why. So BH3 is neutral, but as of right now, that boron does not have another set of electrons, and it is willing to accept another set of electrons, and by definition, that makes it an electrophile. That's why we do this. And this is what we call borane. Borane. Now, here's the problem. Borane's typically a gas. It's also very unstable. It doesn't have a very long shelf life at all. So I can't just order up a bottle of BH3. Doesn't exist. So if you go and you work for a laboratory and then you say, hey, I need some borane, they're going to laugh at you because you're not going to be able to get borane just as BH3 only. There's got to be some other stuff that comes along with it. It kind of helps it keep it in solution. It improves the shelf life of that compound, so that way you can actually work with it. But BH3 as it is, can't just get it. Can't just call up somebody and say, hey, send me some BH3. They're going to laugh. Don't be that type of person. So borane is going to be the electrophile of this reaction. However, there's going to be some other things that are going to be involved in the reaction as well. This is going to be kind of step one here. Yep, it's another two-stepper. So we allow borane to do what it needs to do. And then after that process happens, this is the electrophile step. So after that electrophile goes on to the organic and does what it needs to do, then we need to bring in our negative piece. And that's what we've always done, right? This would be the step where OH comes in, or OCH2CH3 comes in, or that second bromine comes in, or that second chlorine comes in, or in the matter of HBr, the H goes on first, and then that Br minus or that Cl minus goes on second. So this is the same process that we've had over and over and over. So in this step, what we do is that we bring in the negative piece that we want to add on to the molecule. And in hydroboration oxidation, that negative piece is a series of reagents. It really just helps ensure that we get what we want onto the molecule. And what this is OH minus as well as H2O2. All right, so this OH minus Folks, it can't be ordered from a bottle either. You don't just have a bottle of OH minus rolling around. This typically has come from something like NaOH. So don't be surprised if that's what they write on the arrow. They're trying to trick you is what they're doing. They're just letting you know this is the actual crystal that was used to dissolve in order to free up the OH that's present that we need to use. KOH can also be used without a problem as well. Any kind of hydroxide ionic species works extremely well here. And a lot of times we just write OH minus because we assume that you know what we're talking about. And a lot of times they never really clear that up. So if they write OH minus, that's great. You now know why, but yet that OH is not going to come into a bottle. It's got to come from somewhere. Where does that come from? It's typically from sodium or potassium hydroxide. That's where we get it. H2O2, of course, is hydrogen peroxide. All right, hydrogen peroxide, yeah, that stuff in the black container that you buy at Walmart or Target to put on a boo-boo when you get them. That's what we're using here. The problem is that peroxide is typically a 3%. All right, when you buy that into a store, it's 3%. It's watered down. It's weakened. Because the peroxide that we use in a laboratory, 10 times stronger, 30. If you get this stuff on your hands, it's going to actually suck out all the moisture within a matter of minutes, and you're going to be left with an old, crusty, white finger. Yeah, it's pretty nasty. It sucks out all of the moisture. It discolors your fingers and your hands and your arms wherever you get on it. It doesn't matter. Think about peroxide being put on hair. I don't care what color your hair is, that peroxide is either going to, number one, bleach it or make it turn banana yellow. And that's the peroxide that's doing it to your skin as well here too. So if you do get stained in the laboratory and you are using peroxide, it's probably the culprit. So we've got to have both of these typically. And what this allows us to do is add the OH group onto that molecule. And sometimes they'll throw water in here too, just as an extra oomph. This crystal has to be dissolved, and it can dissolve in peroxide, but we can add water to this whole process as well. It just helps us ensure that we are going to put an OH group on it at some point in time. That's all that it is. All right. Now here's the thing with hydroboration oxidation. I told you that these processes happen the same way, and they are. We're adding an electrophile. We're adding a negative piece. That's what's happened every single time that we've done this. But I told you that each one of these reactions will have their own little special thing that they bring to the table. There's a proper use for them. What would be the special thing with hydroboration? Well, if you looked at the mercury, it prevented rearrangement, didn't it? No rearrangement happened at all. Well, what's the story with hydroboration oxidation? What makes it so special? Why do we present it to you? Why do we want you to learn it? Because this is our first reaction that is anti-Markey, anti-Makovnikov. That means hydrogens do not play with other hydrogens. Folks, this is the only time, the only reaction so far that we've seen this happen. Hydrogens do not play with other hydrogens with this reaction. They actually do the opposite of. They go to the playground and they look at the groups that are forming at the playground, and they look at the group that they typically would play with, and these hydrogens say, you know what, not today. Not today. I'm not going to go over there, and I'm not going to mingle in with that crowd because they made fun of me yesterday. They bullied me yesterday. And I'm not going to go over there, and I'm not going to give them the time of day, so I'm going to find a new group of friends. And they go to the other group instead. Folks, that's hydroboration oxidation. That's why we use it. So this allows us to basically, and in this case, we're putting OH on, OH will go on backward. Water and acid, put it on a certain way. The mercury route, put it on the same way. Hydroboration oxidation puts it on backward. H's do not play with other H's. They go to the other carbon instead. And that frees up the other carbon that will end up getting the OH group. It violates Markovnikov's reaction. That is why this one is so special. All right, now, you know a little bit background. Now let's do some examples with it. So we're going to start off simple. That's the best way to start examples. And I'm just going to bring in a CH2 double bond CH2. Simple, sweet, precious. CH2 double bond CH2. And I'm going to react this with what we just talked about. I'm going to bring in some borane, TH3, and I need some THF in order for this to stay in solution. Remember I told you can't just order up a bottle of BH3. You're going to have a solvent, and that solvent is our cupcake molecule, THF, tetrahydrofuran. And then route number 2, we're going to bring in some OHs, but we are not happy with that. We're going to bring in some peroxides that will help out with that attachment, and we're still not happy with that. We're also going to bring in some water just to make sure that things happen the way they're supposed to. So what kind of products get formed? Okay, well, this one's going to be pretty easy. CH2, double bond, CH2. Well, what I do is I break the double bond. You missed that sound effect, I know. Two sides of attachment open up. Folks, it's the same carbons on both sides. It doesn't really matter. What goes on here, though, this is how I want you to think about it. H goes on one side, OH goes on the other. Where does the hydrogen come from? It eventually comes from like the borane and the peroxide interaction that will happen later on down the road. But I want to shortcut this. I don't want to complicate it, and I want you to think HOH, 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 HOH. That's what goes on. Hydroboration oxidation. It just goes on in a backward way. So hydrogen goes on first. Okay, does it go to the left or to the right? These two carbons are the same. It doesn't matter. H goes on one side and OH will go on the other. Bing! There you go. We've just made another alcohol. Goodness sakes, a third way to make an alcohol. Yes, that's true. But this is the only way that we can get the OH group on the end of a molecule. Because all the other routes, hydrogen takes that spot up first. And in this one, it's anti-Markovnikov. Well, in this case, it really didn't matter. That's why I started with this. I wanted you to start thinking about what groups go on to the double bond. And it's H and OH. Now we need a more complicated example. All right, so before we do that, let's look at CH3, CH, double bond, CH2. And let's add H2SO4, H+, and water. What do we get? All right, well, CH3, CH, double bond, CH2. Well, double bond breaks. There we go. And two sides of attachment open up. There they are. And then the H2SO4, this is the hydrogen source. H plays with other H's. So it looks at these two carbons and it says, you know, I feel more comfortable right here. And then that's where it goes. And then the H2O, that gives you the OH group. So OH is going to happen there. Folks, there's a generation of an alcohol. And this is the way that the acid and water has always worked. We didn't do any changes here. It was the same. It was the same that we've always done. Now, let's take that same molecule, but this time use BH3THF and OH, H2O, and H2O2. This is hydroboration oxidation. Well, I can draw this starting reagent again. That's what I'll do here. My double bond breaks just like before. Two sides of attachment open up just like before. Hydrogen adds on first. but hydrogen is anti-Makovnikov. That's the whole purpose of hydroboration oxidation. Hydrogen is anti-Makovnikov. It's got a chip on its shoulder, and it looks at this carbon with those two hydrogens, and it says, no, I hate you. You made fun of me yesterday. You bullied me, and I'm not going to hang out with you today. So I'm going to go over to this other carbon. I know it's not the typical group that I hang out with, but they might appreciate me. And this is where the hydrogen will end up going. That frees up the spot here, and that spot will end up getting the OH from that whole series of OHs and H2Os and H2O2s. Folks, this is a way to get the OH group toward the end. It is the opposite of. If you look at this product from up above and you compare it to this product down here below, you're seeing that OH is going on to the end carbon in this case. There's no other way to do this. H2SO4 in water gives me this product. If I bring in the mercury round will also give me that product. It just doesn't prevent rearrangement. It prevents rearrangement. This is the only way I can get OH in that location. It's backward. That's the point of using it. Now let's go through and name these, just to review. So here's a 3-carbon chain. This 3-carbon chain is propane. And this OH group is attached to carbon number 1. So this is a propanol. And it is a 1-propanol. And there's no other attachments onto this main chain, is there? That's it. 1-propanol. All right, well, if I look up here at this particular product, this is also a 3-carbon chain. So this also is propane. Well, I've got an OH group. So I know that it's not a propane, it's a propanol. And this happens at carbon number 2, no matter which way you number, from the left or from the right. This is also called isopropyl. Isopropyl alcohol. Guys, up in the top, we've just used 1 propane. We reacted it with sulfuric acid and water in order to give us rubbing alcohol that you put on your boo-boos. And it burns. Oh, do I dread it. And then down below, we've used 1 propane, and we've used the hydroboration oxidation step, and we still made an alcohol, but it wasn't rubbing alcohol. It wasn't 2-propanol. It was 1-propanol. That's also called N-propanol, because that's normal. It's the only way that we could get it at this point. My mercury route would have ended up with isopropyl. My water acid route would have ended up with isopropyl. This is the only way that we could have ended up with that OH group on the opposite carbon than what we would expect. Every single time. So folks, this is the story with hydroboration oxidation. Now, there's something else I want to mention. Notice here how I keep writing BH3. All right, well, that's great. Sometimes, though, they might try to trick you, and BH3 is not a very good source like we've talked about before. You can't really hold that into a bottle. TH3 keeps it in solution. That's great. But sometimes they might try to trick you up a little bit, and they might throw in this instead. All right, this group, B2H6, this is called diborane. And this is just called borane up here. As you can tell, B2H6, it would be BH3, and there's like 2 groups of these. That's B2H6. Okay, so that's where this is coming from. This diborane, it's flammable. And it is toxic. And it is explosive. But this is the source of the borane that I need to use in a laboratory whenever I get to this point. So what typically happens here with a manufacturer? Diborane is used at that manufacturing plant. And diborane is mixed typically with THF. Now there's other solvents that are out there that you could choose from. Maybe THF is not the best for you depending on what you're doing with it. So there's a couple of possibilities, some options on the table. So the diborane and the THF is mixed at the chemical manufacturing plant, and that is what we order. So it's typically diborane in THF. However, for reaction's sake, we just write BH3 here, because really what happens is that when they take these two and they mix them together, that diborane will separate into the two BH3 pieces. And THF is just the solvent that keeps all of that together. I mean, that's really all that it does. So it really truly is a BH3 that's taking part in the reaction. But again, sometimes they're going to try to trick you, and they're going to try to put in the diborane instead of the borane, and they will try to squeeze in a B2H6 sometimes. And if so, treat it the same. There's no difference here. It's the same exact thing. It's just written in a different way. It's coming from the same source. We kind of assume that B2H6 is going to give us the BH3 that's needed for this reaction and for this mechanism. All right, so don't let them trick you. That is my take-home message. Don't let them trick you with the boranes. B2H6 is regarded the same as BH3. Now, I want you to bear with me for this. The mechanism of the borane addition is a little complicated. It's probably nothing that I'm going to tell you to write down as far as mechanism goes, but I do think it's important for you to understand the differences and really how this really does add on to the end of a molecule, at least for some background information, if anything else. So what you're seeing on the screen is the first step of the mechanism. You know, you got to think of the Br2, the Cl2, the mercury. The same kind of similar thing is happening here. We see this BH3 compound to come in. We know that that B is the electrophile, and that B is going to get close to that double bond, and we start to see the B kind of hanging out with these two carbons. Well, when this begins to happen, we always had a savior to come in, right? And in the case of Br2, it was that second bromine or that second chlorine. In the case of the mercury, it was something else. But here, it's the same kind of story. Boron grabs onto both carbons, figures out which one he likes better, and the boron is the electrophile. So it still goes to the side with the most hydrogens. It still goes there. And we see a BH2 that shows up on the end, and the hydrogen from a BH3 group, that's going to go here instead. That is why we do not draw the hydrogen on the normal carbon that has the most hydrogens, because it's not the electrophile in this case. BH2 is the electrophile. So ideally, procedure-wise, the same steps are happening. Electrophile goes in. The electrophile attaches to the carbon that has the most hydrogens. The confusing part here is that hydrogen is part of this ensemble. And that hydrogen from a BH3 is kicked to the curb, and that hydrogen goes on to the spot that's left over. And that is why the hydrogen that we're concerned with is not written on the carbon with the most hydrogens. That's because boron has taken that space. There's no room for that hydrogen to go there. Now, that process continues. This is where this gets a little weird. This BHR, this is from the first round. That's still swimming around in solution. There's still double bond in that solution. And this alkyl borane does the same thing again. So boron comes around, grabs onto those two carbons, says, which one do I like? I'll do the normal electrophile thing. I go to the side that has the most hydrogens, and pop, there it goes. Well, this boron says, you know what? I've got a hydrogen here. Two of them, actually. And this hydrogen can be slapped onto that carbon, and this forms the anti-Markovnikov step. So we see the hydrogen again being on the inside, not on the outside. Well, this dialkyl borane is swimming around in solution with more alkene. And this dialkyl borane now brings to the party one more hydrogen that it wants to get rid of. And that boron does the same thing. It grabs both carbons and it says, which one do I like better? And it looks at these two and it says, well, I do the normal electrophile thing. I'll add to the one on the end. I'll go to the carbon with the most hydrogen. And that's where it pops up there. And then it takes that third remaining hydrogen and it slaps it to the left-hand side. What we end up now with is called a trialkyl borane. So this borane does the step 3 separate times. It attacks a new alkene every single time that it happens. It's almost like a chain reaction. It's almost kind of like having or drinking or tasting or eating something for the very first time. And you realize, oh my gosh, that was so good. I want more of it. And very early on, one of my nieces actually loved key lime pie. I made a homemade key lime pie, and she ate a piece of it, and she loved it. Very young. And then before I knew it, I turned around, and she was in the kitchen, and she was eating the entire thing. Well, a few moments later, she went to the bathroom, and she threw it all up because she gorged herself on it. That's what borane is doing here. It had a little taste. It loved what happened. And the boron is coming around again and again and again. And it's getting more and more and more until it satisfies itself. Well, we hope it doesn't go to the bathroom. We hope it doesn't throw it up. But it's getting ready to. Boron now is loaded down with these 3 R groups. These R groups are the alkyl groups that's part of this whole reaction scheme. That's kind of what I started with. The double bond piece, that double bond's been broken. That is the R group that's carrying with it. All 3 of these are the same. And this is one of the reasons that we have to add so much OH source. OH from a solid, H2O2 from peroxide, H2O, water. We do all 3 of those. Because what we want to happen in this step, ping, 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 all 3 of those leave boron. It just pukes them right back up. When that happens, a little bit of stimulation has to go on, and these R groups get bonded up with OH groups. That's the sources here that we are seeing on the arrow. This R has an OH, that R has an OH, this R gets an OH, and it's in the spot that boron was taking up, which is in that very first electrophile stage. That is why this is anti-Makopnikov. So we get 3 alcohols from this reaction. This is not a 1-to-1. And then we get a boron that now also has some OH groups that's there due to all of those OHs that we have introduced into the system. How does that actually happen? Here's the mechanism. Again, I don't want you to copy this. I don't want you to regurgitate this on a test, but I think it's important for me to at least show you some of these curvy arrow mechanisms that begin to happen. So here's the boron with the 3 alkyl groups. Here is a peroxide ion that's coming in. That peroxide is a negative charged, and you're seeing that negative attracted to that positively boron. When this happens, boron now has too many bonds. It doesn't like it. It becomes negative. It's got to get rid of something, and boron says, you know what, R, you got to go. So this R group begins to leave, and it goes off and makes a OH. And then that process repeats, and then that process repeats, and then finally we end up with the 3 ROH groups in the end. All right, folks, again, just a brief little moment of time in the mechanism part, but do not stress over this mechanism because honestly, I'm not going to ask it. Overall reaction, this is what we see. If you wanted to kind of write down the steps in a little bit more detail than normally what we would do in these reactions, you would start with your alkene. Notice it's going to take 3 of those in order for it to work. You're going to add your BH3 and THF, and you'll get the trialkyl borane that happens here. So the double bond breaks, and that releases CH2, CH2, CH3, and that's what you're seeing here. There's 3 of them. Boron will grab all 3 at once. And then we add on all of our OH groups, and then when that happens, all of these groups begin to spit off of the boron, and where that B is located, that is where an OH is going to go. So CH3, CH2, CH2, and then OH goes on. And notice we end up with 3 of those as well. So we start with 3 alkenes in order for the reaction to go forward, a ratio of 3 to 1, and then we end up with 3 alcohol groups in the very end. All right, so in the next video, we'll do some of these examples. We'll do more of them. I want you to feel more comfortable with these. You know, sometimes this can get muddy. I know. Sometimes we start talking about mechanisms and curvy arrows and we just get lost, and that's not a big deal. It's normal. It happens. But I want to come back and I want to talk about predicting products. Just full-blown, here's their alkene, what product is going to get formed. So that's what we'll do in the next video.